Indoor climate influences everyone's well-being. Buildings consume 40% of the world's energy, with 50% used by HVAC systems. To create a more sustainable world and comfortable indoor climate, it is critical that we heat and cool our indoor spaces efficiently. Demand for heating and cooling depends on the external climate, which varies globally. Yet there is a common pattern as demonstrated in these three graphs from three international cities. The graphs illustrate the heating degree days over a 3-year period, where peaks are the coldest days requiring the highest power output for the heating of the building. The graphs make clear that only a few days require peak power demand. Let's look at 1 year in Brussels. We can assume that the highest heating degree day represents 100% power demand. So the coldest day that year is when we use the most power. We only spend a few days at 100% power demand. The majority of days require only partial load. For example, in this specific year, 30% of the year requires 0 to 25% power, 31% requires 25 to 50% power, 17% requires 50 to 75% power, and only 2% of the year requires 75 to 100% power. During the example year of 20 and 21, 61% of the operational time was spent below 50% power. Efficiently running the system in reduced power for such a significant time is critical to controlling running cost. With this in mind, let's examine how we heat and cool buildings. Hydronic systems have certain characteristics relating to the power emitted from each terminal unit. The graph on the left illustrates the relationship between flow and power. To reduce the power emitted, you reduce flow through the terminal unit. As you can see, this is a non-linear relationship because as we reduce flow, we increase the time taken for the fluid to pass through the terminal unit and heat the surroundings. Therefore, the power emitted is not linearly related to the flow going through the unit. For most of the year, the power demand is below 50%, working with flows below 20%. Therefore, to achieve energy efficient indoor climates, we need to accurately control flows below 20%. Although this principle applies to all heating types, let's see how this works for an air handling unit. The unit has an air intake which draws air through the filters, over the heating and cooling coil, and then emits air at the desired temperature. In this example, the AHU is designed to manage an intake temperature of -10 degrees C and achieve an output air temperature of 21 degrees C. In this condition, the heating coil requires 100% power and 100% flow from the control valve, both simulated in the graphs. Water is passing through the coil with a supply temperature of 60 degrees and a return temperature of 45 degrees C. If external temperature increases to 5 degrees C to achieve the desired 21 degrees C, the power supplied needs to be reduced by limiting the flow through the unit. As you can see in both graphs, the flow reduces, the temperature of the return water reduces too, causing the non-linear relationship between power and flow. The flow is now at about 20% of the design flow, and power output is about 50%. Systems usually operate below this point, so the valve must adapt to changing demands throughout the day. Accurately controlling flow is critical to achieving optimal indoor climate and improving energy efficiency. TA Smart delivers high accuracy over a broad flow range. It provides accurate control down to 0.5% of the nominal flow. Valves that perform badly at low flows risk operating in an on-off manner. With poor accuracy at low flows, the system controller will compensate for temperature fluctuations by opening and closing the valve. With high accuracy low flow regulation, the system controller can operate as designed and deliver a consistent optimal flow.